For those of you that were in Vegas over Halloween and missed it. Okay. I'd forgot that. I thought Rachel was just mad at me, but no, she's getting married to Elvis. No. All right, so what we've studied so far is that R is equal to some or tau, torque, is equal to some R crossed with an F, okay, which is basically R, the perpendicular R times F, or R times F sine of the angle between them, okay? All right, so, and that gives us a torque, all right? And things go, you've got a positive torque, which means it's making it go counterclockwise, and a negative torque, which makes it go clockwise. And if things are in equilibrium or not, then the sum of the torques equals, here we go, the sum of the torques is equal to I times alpha, which is a lot like the sum of the forces is equal to ma. In fact, the two are very much related. Okay? And I think we looked at enough of the homework problems, so we knew that now. I is what is known as the moment of inertia. It is just like moment of inertia. It's the same concept, the same idea as inertia of mass, but this is the moment of inertia. Moment of inertia, which means it's some odd, like here's a nice disk. Discs are kind of easy to spin, especially if they're like this. They're easy to roll like this. But if I had a square, you know, that wouldn't be a very good wheel, right? Okay, so it's got a little bit higher moment of inertia. It's harder to get it to turn, right? And those are things, resistance to turning, to going in a circle. And then all those other equations apply for going in a circle. Like we have theta equals the average radians per second times t. We also have that theta equals the plus 1/2 alpha t squared. And we also have omega final squared equals omega naught squared plus 2 alpha times theta. And theta is in radians, omega is in radians per second, and alpha is in radians per second squared. And the big idea from putting these two things together is that when something rolling without slipping, this is, we're just kind of getting warmed up here. Rolling, so we make a mistake. Rolling, slipping, rolling without slipping, as I'm talking directly to the board. Okay, rolling without slipping is these two things hold. V of the center of mass, the velocity of the center of mass, equals R times omega. Okay? And or the tangential acceleration equals R times alpha. That is rolling without slipping. All of our problems will deal with rolling without slipping. Okay? So there's an overview of what we've learned so far. Okay? All right. Now, so now, let's take a look at this really tricky problem. All right? Your first problem that has the last of the rotational problems that I gave you. Here it is. Here we go. And then we'll look at problem 50, 54, and 57, and then we'll call it a night. All right? Okay, so here we go. This is problem 39. This is one I assigned you. Oh, by the way, in case you didn't get the email, everyone's homework's been extended until Monday. You don't have to do it tonight. All right? Because I understood there's all kinds of bio tests and everything out there. So Monday, you get to Monday, turn it in. I didn't extend the other ones yet, but that'll probably happen too. I like this new program because I can extend homework. So the old one, if I extended it, it wiped everybody out that had already done it. So it's the little people pleasers were getting upset with me. All right, anyway, here we go. Here's our problem. We've got this pulley, Okay? Got this little pulley. And it's going to be having an angular acceleration that way. Now get used to the terminology too. Angular velocity means omega. Angular acceleration means alpha. Okay? The angle that it goes through is theta, and that's in radians. All right. So it's going alpha, but it also has this permanent little torque going this way. It has this permanent little torque going that way due to the friction in the wheel. Okay? Now what's making this thing turn? Here's what's making this thing turn. We've got a rope here, and we'll just extend of T2. I got a tension of 2, and of course it's extended down here to this 0.8 kilogram block right here, which will also have a 0.8 times G going that way. All right? So this is T2. This has a radius of has an R equals 0.15 meters. The mass of the pulley is equal to 0.2 kilograms. All right. And then it's also got being tugged this way by a T1, which is being caused by this 0.4 kilogram thing. So I've got T1 going up this way and 0.4 G. All right. Two things missing here. I got two things, but it's the same thing missing here. My acceleration. And that's what I want to find out what the acceleration is. There we go. There we go. I assigned this problem, and then I was like, why did I do that to him? I'm just going to wind up doing it in class. So that's what we're going to do. All right. Okay, so here we go. First thing I do, I want to find A. That's what we're after. First thing I do is, unlike the pulley problem that you had for the test, this time where we broke it into the two pieces, I've got three pieces I've got to look at, okay, that will provide me with some guidance here, okay? All right, because the reason is when we had that good old frictionless pulley, or really not even a pulley that just spun freely or didn't even spin, it just didn't have any friction at all and the things went up and down, there was no energy loss in this pulley. So this pulley, this system actually is going to make things fall slower, which makes sense to us. If you have a pulley in there, it's going to fall slower than if I just kind of put these things over a cube of ice, right? Or some of the round circular piece of ice, and just go flying. But with the pulley, it goes a little bit slower. All right, so here we go. So let's look at the pulley. Well, the pulley, since it's going round and round, I'm going to take the sum of the torques. You might be going, sum of the torques? What are you talking about? Yeah, we got torques here. Because it's going in a circle that equals I alpha, which is going to equal, these two guys are causing a torque. T2 is, what kind of torque is that? That's going counterclockwise, so that's positive. T2 times R minus this torque here, T1 times R, minus this little torque of friction which they gave us in the book, which is 0.35 meter newtons. They don't say Newton meters in this book because they don't want you to get confused with work, with the joules. So it's 0.35. Okay. Well, there I've got one equation and two unknowns. Now, that was just this little frictional force here in the pulley that's permanently there. It's always there. Okay. Good question. Now, well, I've got T2 and T1 are unknown. What about I? I is known. I of the pulley, since it's a disk, is 1/2 mass of the pulley times R squared. That's the I of the disk. And If I is not given to you on an exam or something like that, I will provide it. I don't want you to memorize that sheet of the different moments of inertia that's in your book. Okay, I'll either have that sheet attached to your test, to the back of the test or something, or eventually you just kind of pick up things. We're always going to deal with hoops, spheres, or solid discs. I mean, that's pretty much it. Or rods. Sometimes we got rods for the most. Okay, now we also have this alpha. That's not known either. But this thing is rolling without slipping. So can I get A in terms of alpha? Can I get the acceleration? Because this acceleration A here is going to be the same acceleration that's being, the tangential acceleration that's going to be experienced there. So I can turn alpha into that same, this AT is the same as this A. So I can turn this alpha equals AT over R, or just A over R for this case. So I'm going to say this. I'm going to say, all right, well, this equals 1/2 MP times A over R. Oh, my gosh. Look at this. This is a mess. Equals T2 R minus T1 R minus 0.35. Okay, now, that's not right. Y'all let me put up something bogus. There we go. I forgot that little R squared in there, because this is I times alpha equals all that. Now, okay, I took the most time with that. Now let's take a look at this guy. So let's look at the 0.8 kilogram pulley, all right, or 0.8 kilogram block. And he is equal to the sum of the forces in the y direction is equal to T2 minus 0.8 G, which equals negative 0.8 times A. Great. So T2 then equals 0.8 G minus 0.8 A. Now you see where we're going with this? We're figuring out T2, so I'm going to take these two guys and stick them right here. So now let's take a look at the 0.4 kilogram, because I need this T1. I need to get a term for that T1. So I get sum of the forces in the y direction is equal to T1 minus 0.4 G equals, now he's positive. He's going up. Equals 0.4A. So T1 equals 0.4A plus 0.4G. All right. We've almost got this all worked out. The rest is just an ugly algebra. Because watch what happens. Watch the miracle that happens. I had three unknowns, basically. I had alpha, T1, and T2. I used this equation over here to give me something for alpha. And I used these, so that's one equation. And then I used these two equations to give me something for the tension. So there's the two other equations, because I had three unknowns. So I needed three equations to be able to solve them. So now I've got them. So this will equal, so when I do the substitute T1 and T2. Okay, so I've got 1/2. So here we go. 1/2 MP R squared over A over R equals T2 is equal to 0.8 G minus 0.8 A times R minus 0.4 A plus 0.4 G times R minus that 0.35. There we go. Now look what we have here. First of all, It looks ugly. First thing I'm going to do is, they gave us R, it's 0.15 meters. But let's go ahead and divide R out of everything. And something amazing is going to happen here. Let's divide R. So I'm going to divide R, and if I divide that by R, divide this by R, divide this by R, and I also have to divide him by R. Can't forget about that. Okay, look what happens here. I get R squared times R, so those go away. That's nice. This goes away. This goes away. And so I'm left with 1/2, and the mass of the pulley was 0.2 kilograms times A equals 0.8 G minus 0.8 A minus 0.4 A minus 0.4 G minus 0.35 over R. There we go. Now it's something manageable. We'll stop there. We'll stop with the last little, just a matter of putting it all together. In other words, we can collect up all the A's on one side and all the G's and the 0.35 divided by 0.15 on the other side, and basically you wind up with, if these are your numbers, you wind up with about 1.2 meters per second squared is what it accelerates at. That's the A. Whew! That's a lot of algebra. This is algebra-based physics. That's why they call it that. Yes, Lauren?
Why did the A's go from it being added together to being subtracted? Or 4A plus 4G went to 4A minus 4G?
Oh! Aha! Miss Crunchmeister rule. What happens when you got a negative outside the parentheses and you drop the parentheses? Negative, negative type thing. That's what happened. Good question, though. Did you have a question, Eric? No, you're just taking it all in. All right. Blake, you're good? Oh, okay. All right. I thought you were going, well, if Eric doesn't have a question, I do. All right. Now, so that's a very difficult problem. And I'm not going to make any, I'm not going to say you'll get one of these on the test. Nah, the ones on your test for the rotational part, they'll deal more with these kinds of guys and stuff, and making sure you know this relationship. You know, I'm not going to do this to you on a test. We will, though. I guarantee you, what's going to happen on a test is this time we're going to have a rolling hoop is going to smash into a spring. So let's get ready for rolling hoops smashing into springs. Just like we had the sliding block that smashed into the spring that screwed everybody up, I'm not going to let you get off the hook. You're going to do it again. Some of you did just fine with it. But, so that gets me into, what does all this have to do with energy? Here we go. There's work being done here. Now, torque is really not doing the work. Torque doesn't do work. All right? Because when I twist something, the vector is going this way, and the thing is moving that way. So that's at a 90-degree angle. That's perpendicular to it. That's not doing any work. However, let's take a look at the situation where, and then we're going to do this problem. We're going to look at this problem. Let's look at the situation where Dad is pushing the merry-go-round. All right? And you're running around the circle. All right, and you're going in and you're providing a nice constant force to this thing. Now you're doing work because you're moving something a certain distance around that circle. All right, so that's work being done. And whenever there's work done, especially if you start that merry-go-round from 0 to going to some omega spinning around, you've done work to get it to do that. You've done a change in kinetic energy. Uh-oh, here we go. We've got a new kinetic energy thing. So let's set it up first. Work, now this is going to look funny, is equal to tau times theta. Looks like a new sorority or something, but it's not. This is work. Now you might be going, what the heck? Where does this come from? What tau times theta? How does that work? That doesn't look like, oh, I better make this, I'm going to make this more spiky so it doesn't look like my omega. There we go. Nice spiky work. All right. So, well, where does this come from? And we also knew that work is a change in kinetic energy. What is this kinetic energy? Well, there's a change in the if it starts from rest, there's definitely a change in the tangential velocity, right? It's 1/2 mv squared. It's got a final mvt squared. Wow, there's one. All right. There's also, let's take a look at what torque is. Remember, torque is F times R. Okay, so this is F times R times theta. Oh, wow. Well, that's kind of cool. So down here, look, what's R times theta? What does that equal? That's from Chapter 7 homework. R times theta, 2 pi r, circumference, right? That's your S. That's your distance S. Oh, so I've got a force times a distance. What's a force times a distance? Work. There it is. Ta-da! That is so cool. And notice that this work is actually going around the circle. It's actually, that work is always following, is always parallel to the displacement, the force that you're providing there. So therefore, it's force times that distance going around. Okay. All right, but this also equals, now remember, we also had this, go back to this guy, tau times theta. We also had tau was equal to, the torque was equal to I times alpha times theta. Oh my gosh. Now we got a mess on our hands. Well, alpha times theta, okay, now put your pencils down. Just, this is one of those, it's kind of like art sometimes. You just got to let it flow over you. So that's what we're going to do with the physics right now. All right, just trust me on this. That, well, let's take a look at these two guys. Let's take a look at this alpha times theta. And let's come over here and go, oh, I've got an alpha times theta right here. Let's play with this a little bit. Omega minus this equals 2 alpha theta. So so if I divide both these by 2, now we're getting somewhere. Look at this. This is starting to look like something, isn't it? It's starting to look like some kind of kinetic energy, possibly, but not yet. So we're going to take this and substitute it in here, and we get I times 1/2 omega final squared minus 1/2 omega naught squared. And now we stick the I in for both of those, and we wind up with this. 1/2 I omega final squared minus 1/2 I omega naught squared. And guess what? That's your change in kinetic energy. So we've got a lot of stuff going on here. A lot of different ways of looking at things. All right? So we can make these relationships. We can say F times S is equal to 1/2 I omega final squared minus 1/2 I omega naught squared. Or we can say tau times theta, F times R times theta is equal to all this. Or we can say tau times theta is equal to all this. Or we can say I alpha times theta is equal to all that. Any one of those four. Okay? They all came from the same place. It's just a different way, you know. Basically, this is Robert, this is Bob, this is Bobby. It's all the same thing, you know. Okay. And I couldn't think of a fourth one. Bubba, if we're in the South. All right. All right, so let's take a look at some of your problems from this. Already you're starting to get glassy-eyed and petrified of this, and it's not that bad. So let's take a look at a few of your problems. And we'll talk about conserving angular momentum next time, which is basically the ice skater, arms out, pulls her arms in, or his arms in, they spin faster. By the way, what's the #1 show in Canada right now? It's Skating with the Hockey Stars show. I'm serious. This is #1. All these retired. The producer said, "Hey, we've got all these ice skaters, female ice skaters, that are in like ice capades and stuff like that. That are real ice, that are kind of known entities. We got all these retired hockey players up here." And so they kind of do a Dancing with the Stars, but it's hockey, and it's like huge. The hardest thing the producer had to do was to get the hockey players to do it, but eventually they did. So anyway, all right. So what that had to do with it? Did you all have problem 50? I think your homework. I think you do. Now this, so listen to how this is read. It says a constant torque of 10 newtons. Okay, so a torque of 10 is applied to the rim of a 10 kilogram uniform disk of radius 0.2 meters. What is the angular speed of the disk about an axis through its center after it rotates 2 revolutions from rest? Oh my gosh. Basically, here's the deal. Here's what they're saying. I'm going to apply what they want. I don't even know what they're asking for. What's the angular speed of the disk? Oh, they want to know what the speed of the disk is when it's done spinning. Okay, after 2 revolutions. After 2 revolutions. They gave us a torque, and they want to know the final speed, the final angular speed. Okay, so they gave us a torque, they gave us a distance. It started from rest. I think we've got it right here. Okay, so that's the way I want you to do these problems, is I want you to look at them and line up with these 4 things. Remember, all 4 of these things are going to equal this thing over here. So if we look at this problem, we go, oh, okay, I've got a torque, that's tau. I've got a radius, well, I'll be able to figure out the radius from, what's its angular speed about an axis through the center after it rotates 2 revolutions from rest. Okay, I've got tau and theta. Piece of cake. And so, so for problem 50, what I would do is I'd just say, okay, I've got tau times theta equals 1/2 I omega final squared, because it started from rest. Tau is 10 newtons times theta. And by the way, once we multiply it by that theta, it becomes a scalar. It becomes a scalar. Okay? All right, so then we've got Newton meters. So we got energy. All right? Now 2 revolutions. What's that in radians? 2 revolutions. 4 pi. Yeah, there we go. 4 pi. Okay. So that's 4 pi equals 1/2. Now it's a uniform disk, so you have to go look up what the moment of inertia of a disk is, what the I of a disk is. And you get 1/2. It is 1/2 m r squared. They gave us m and r. That was nice of them. Times omega final squared. Hey, we know all of this. We know all of this. This is the only thing we're missing. Piece of cake. Piece of cake. I did it much harder in the afternoon class. See, I got to rehearse with them, confuse them, and then we get it. Then I finally know what I'm doing by the time I come in here. That's always good.
Where did the I come from?
This I, that's
No, the value for I, the 1/2 m.
oh, that's a disk is 1/2 mr squared. A sphere is 2/5 mr squared. A rod is 1/3 mr squared type thing. You just, after a while, you just kind of start to know these things, which is kind of scary. All right. So, well, that one wasn't bad. That was a piece of cake. Now, let's take a look at problem 54. Okay, this is a dad question. You wish to accelerate a small merry-go-round from rest to rotational speed of 1/3 of a revolution per second by pushing tangentially on it. Oh, by the way, there are some funny YouTubes of people messing around with merry-go-rounds. You know, because one thing that you could do, this is unrelated, but it kind of gets into what we'll talk about Tuesday a little bit. If you got a bunch of people like uniformly spread out over here on a merry-go-round, they're going around. Its moment of inertia is a little bit different, right? It's got a different moment of inertia, all right? Because it's got a different, its center of mass is changed. You suck in that center of mass, okay? You shrink I, because here's basically the end of the chapter. I kind of got off track here, but basically this is the deal. You've got I naught omega naught equals I final omega final, which is angular momentum, just like mv initial equals mv final, all right? But if I is real big, I naught and omega naught is kind of small like this, and then all of a sudden you make IF really small, what's this omega final going to be? Huge. So if you get a merry-go-round kind of going, and you have enough, and it's not going so fast that the centripetal force keeps you from, you can't get to the center. If 3 people all said, hey, let's go to the center, it'll get going really fast, you'll throw this guy off. You used to kind of see some of those things on YouTube. Anyway, because they shrink the eye, and then this guy doesn't know about it. He's like, whoa. All right. Okay. Well, shoot, there's the end of chapter 8 anyway. All right. Well, let's talk about problem 54, where we have the merry-go-round, and Dad is wanting to push on this thing, because it's one of your problems, and then we'll end with the hoop. Okay? And you wish to accelerate a merry-go-round from rest to a rotational speed of 1/3 of a revolution per second. What? 1/3 of a revolution per second. And it's also, I'm going to leave the rolling without slipping up there. Okay? So, 1/3 of a revolution per second. What is that? How far is that? 1/3. Oh, so of course he instantly writes 1/2. All right? 1/3 of. What does of mean to do? Multiply times 2 revolution. 2 pi. Oh, it's 2 pi over 3. Well, that's not bad. That wasn't bad. So this is our omega. This is our omega final. And when you punch this in, it's 2.9 radians per second. Okay? So Dad wants to push this thing to get it going. That's our final velocity. The merry-go-round has a mass of 250 kilograms. Has a radius of 1.5 meters. Ignoring friction, thank you very much. So all forces are conserved, so these things will work. So ignoring friction, how hard do you have to push tangentially to accomplish this in 5 seconds? Oh. Okay. All right, well, here's what they want. They want us to know what the force is. They want us to use this one. Now remember, this S, this isn't seconds, right? This is the arc length. Okay, so don't get that confused. We got to figure out that arc length. Because I know this guy's 0. I've got all these numbers, but I don't know F and I don't know the arc length. However, I do have the equations I just erased. That will help. All right. So let's take a look at this. Okay, so here's what we're dealing with. We're going to be dealing with this, but first we've got to find S. All right? So he went in 5 seconds. At least they gave us a time. At least they gave us a time. So it went from 0 to 2.09 radians per second in 5 seconds. So I've got it, and we're going to assume, since it was a constant force, guess what we're going to assume? Is a constant angular acceleration. So therefore, theta is equal to the average omega times the time, which they gave us. T was 5 seconds. So I can go, oh, okay. Well, that's not bad. Then the average omega is 0 plus 2.09 divided by 2. So you get about 1.045 times 5. 45 radians per second times 5 seconds. Hey, I love it when a plan comes together. Look, the seconds cancel. I'm left with radians, about 5 of them. Okay? So, that was supposed to excite me for some reason. Oh! I've got this far, and I know R. They gave me R. So now I can finish this problem. So let's go ahead and finish it. I'm going to erase 50 and put 54 up here. So we've got this far. Okay, so we're going to look at this guy. We're going to say, okay, well, F is equal to 1/2 I omega final squared over R times 5 radians. Okay, now, since it was a disk, then I, and it's uniform, solid uniform disk, then I is equal to 1/2 250 kilograms, and it was 1.5 meters times 1.5 meters squared. And we wanted it to get going, so this would be 1/2. It'd be 1/2 of all this stuff. So this equals 1/2 of 125 times 1.5 squared, which is 1.5 squared is what? 2.25. Right? Think? Yeah. Sounds good? 125 times 2.25 divided by 1.5 times 5, which is 7.5. There you go. Something like that. That's the force. So it's about 250, 125 divided by 7. Yeah, that's about right. 125 divided by 7, about 20 newtons, right around there. No, 18. Not very much. I don't know. Shoot, that could be all wrong, too. Hey, I got you to here. You're on your own after that. All right. Okay, now, as Curly would say, for the coup de grace, here we go. Bugs Bunny say that too. But here we go. Let's talk about a hoop. I've got one other thing I need to show you all before we can talk about hoops rolling down inclines. It wouldn't be Physics 1 if you didn't have inclines and sliding blocks and rolling hoops. I mean, that's just, and then if you stick around for Physics 2, that'd be 16 weeks of rolling hoops and sliding blocks and inclines, and then about 15 weeks of E&M and light and everything else. Then we finally get into relativity and quantum after about 30 weeks of physics, and that's the cool stuff. And that's when people start to like it. They're like, why? Wow, this other stuff was kind of cool. I'm like, yeah. We should start with relativity and go backwards. But we don't. because they think you have to know this stuff first, and maybe you do. All right, so here we go. Here's the last thing I needed to tell you all. So rolling, keep that idea of rolling without slipping in mind. Remember, if it's rolling without slipping, then the tangential speed of the center of mass, or the velocity of the center of mass of the wheel, is of the axle. In other words, if you watch the axle go by, is equal to r omega, and the acceleration, if it is speeding up, if that thing is speeding up, then the tangential acceleration is equal to r times alpha. Rolling without slipping. Okay. And the reason is, let me just back up here real quick. The reason is, like a few snowy days, I've been, one of the ways I get here from the Northland, well, it's the only way to get here from the Northland now that the Paseo Bridge is completely out of commission for the most part, is go 435 to Eastwood Trafficway, then you go up Prospect, and to 51st Street, cut across, and all that kind of stuff. But anyway, when you're going up that hill, or if you go all the way down to the Paseo and make a left, and you go up Lydia, that way, it's a real steep hill, and on snowy days, people have trouble making that hill. So their wheels are going really fast. So they've got this. So if V equals R omega without slipping, then V does not equal R. All of a sudden, if this omega is real big and V's real little, but R stayed the same, because their wheels are turning really fast, but their axle's not going anywhere. So that's causing slipping. So these two things aren't equal anymore. All right? But if there's no slipping, then this is nice translational speed. All right. What a mess. Wow. Okay. Now, and the acceleration is the same thing. Now, let's talk about a hoop. But first, you need to know this. Who's this guy? What? Kinetic energy. Translational kinetic energy. Now we got to add an extra word to it. Translational kinetic energy. What's this guy? Gravitational potential energy. Who's it? And then everybody's favorite from the test. What's that one? The spring. It's the elastic potential energy in the spring. Or it could be when we'll also look at Young's modulus and stretching of materials, the stretching and smushing of materials. This actually applies to Jell-O, and we'll get to that later on. All right. And now, last but not least, you got this guy. Moment of inertia times omega squared. That is your rotational kinetic energy. So get that in your mind. So when you're reading about these things, rotational kinetic energy and mechanical energy, as long as everything's conserved, there's no, it's kind of a strange thing. The rolling without slipping, you can't do that unless you have friction. All right? But it negates the frictional force. It makes the frictional force conservative, actually. Well, that's probably bad physics. I'd erase that, Hao and Tingyi, that I said that. But if it's rolling without slipping, then the forces are conserved. Okay? And so we're going to have E final equals E naught, E initial. Okay? So now we are ready for this. And here's where we're going to end. I think you have a problem 57 where you have a hoop. Okay, and there's his center mass. Now he's a thin, if you see a hoop, that is a thin hollow disk. All right, that's a thin hollow disk. All right, got a hoop up here. He's 1.2 meters high. He's got a V naught of 0. He's got an omega naught of 0. I before is going to equal I after. So we're just going to leave the I's alone because he's a nice rigid body. All right. Our I before and our I after, if we were like a clown launched out of a circus cannon, could actually change because we can change our center of mass and we can change our I. All right. Okay. And the initial height is 1.2 meters. And what we want to find is its final velocity going down the hill. What is that? We just do it like we did before. Good old chapter 5. I know it's everybody's favorite chapter, that energy stuff. You loved it. Tore it up. Energy before equals energy after. And you'd leave class, you go, okay, you beat that into our heads, it makes sense. You'd read the problem and go, I don't see any energy before, I don't see any energy after. What are they doing to me? They're killing me. But hopefully this way we'll be ready, we'll be armed. So we want to know its final velocity at the end. So we just go, oh, okay. Let's change this a little bit. Let's do it this way. So let's just start from the, Julie Andrews. Let's start from the very beginning. Very good place to start. Or Tina Turner. We're going to begin nice and easy, and we're going to end rough here. Okay. All right. Plus. Oh, do I need to, is there a spring involved here? No, but boy, I can tell you this. On your exam, you're going to have a bowling ball that's going to be rolling flat. So we'll throw this guy out. It's going to be rolling flat, and he's going to smack into a spring, because we all kind of screwed that up last test. So you get a chance to redeem yourself. But this time you're going to have to add the rolling energy. Okay. All right. And 1/2 I omega naught squared. Okay? There we go. Now, this equals 1/2 mv final squared. Now this v is the velocity of the center of mass. That's the velocity right there in the middle of that wheel, which is suspended in air. But you can have the center of mass of the thing doesn't necessarily have to be on the thing. Like center of mass of a donut is where the hole is. All right. All right. Plus mgh final plus 1/2 I omega final squared. Now, let's throw out what we don't need. This is 0. This is 0. This is 0. So all I'm left with is mgh naught equals 1/2 mv final naught plus 1/2. Okay, this is a hoop. So I'm going to put in the I right now. Okay? And the I is mr squared for a hoop. Okay? That's I times omega final naught. Okay. Now, this problem, we can nicely, we can divide out the m's. We can get rid of the m's. But you know what they didn't give me? They didn't tell me what r was. Uh-oh. But guess what? I don't need it. You know why? Because this thing's rolling without slipping. So therefore, let's go ahead and get rid of the m's first. I'm going to hold you in suspense for a little bit longer how we get rid of the r. So I got gh naught equals 1/2 v final squared plus 1/2 r squared times omega final squared. Now, George, I'm in trouble. I know these two guys. I'm after him, but what's this guy doing? Is there any way to get rid of that omega final? Rolling without slipping. Rolling without slipping. What's that? Yeah. Exactly. Oh, not acceleration. Speed. Yeah. The VCM, which is also VT. Okay? For when you're going around a circle. In other words, there's VT. But it's also VCM. Okay? All right. So, yeah, there we go. So V, the final V actually equals R times omega final. So omega final equals VF over R. If I square it, aha! Look, looky, looky. So I stick them in. I get GH naught equals 1/2 VF squared plus 1/2 R squared VF squared over R squared. Yada, yada. Gone. Boom. And look, I can add 1/2 and 1/2 all day long. So I get GH naught equals VF squared. So VF of the hoop is equal to square root of GH. Uh-oh. Notice, it makes no difference how big the hoop is, as long as it's very thin, okay, and it's rolling without slipping. It'll be going whatever G times H naught is when it gets to the bottom. Now, this is different than our sliding block. Our sliding block problem with no friction V final was equal to the square root of 2GH. This is bigger than this. Why? Look at how's doing it, because there's more energy, there's energy being lost there. He's got to share that energy. The mechanical energy has to be shared now with what's making it roll. That's why we're real careful when we assign at the beginning. That's why physics teachers have to be real careful when we assign problems at the beginning, that we don't have like skates and roller coasters and stuff like that, because there's some rolling friction there, or there's some rolling energy in there in the problem. That's why we always use sliding blocks, okay, so that you can get the initial thing. Wow, that's impressive. If we know all that, but really, it's just it just looks ugly, but it's not all that bad. And we talked a little bit about the conservation of angular momentum. I think you guys are pretty much done. I can tell by looking. You've pretty much had. All right, if anybody wants to do extra credit, you can look at problem 63. 63 is a favorite of mine. I'll make sure I send that out to you all. It's one of the reasons we don't have, or basically it's this thing with a little ball coming down there, rolling down there, and trying to go through a loop-to-loop, like an old Hot Wheels set. Love that Hot Wheels set when we go through the loop. That was the bomb. Then you had the little like energizer at the bottom. Send it around again. You were cool. All right. Anyway, that was back before video games. All right. That's all I've got for you. Have a safe weekend. My stepdaughter's getting married Sunday, so that should be fun.